Yes, sir.
right? And we can just try to attempt a proof of that, which is a kind of means I don't know the complete proof, but I know it's based on something in graph theory. So it's very interesting. Means it's combinatorial.
Yep.
So yeah, let us just have a look at it, because this theorem is important, but at the same time, the proof is very interesting. At least one of the proofs is very accessible, I think. Schroeder-Bernstein theorem. All proofs are interesting in their own ways, but one proof is very elementary, I think. So do you remember the statement of this? Do you recall the statement?
Yes, sir. If F is injective, then it can be. Uh, then there exists. Oh, 1 second, sir. I'm trying to. Uh, yeah. If we have F from A to B,
Huh?
such that. Uh, so
Is
it's
inject.
basically like cardinality of A greater than or equal to B and cardinality of B greater than or equal to A implies that cardinality of A is equal to cardinality of B.
Correct. Where cardinality we can define in terms of injective
Yeah.
functions, right?
Yes.
So
Yes.
that basically just says that if F is injective, which means cardinality of B is greater than cardinality of A, or
Yeah.
greater than or equal
Equal to.
to,
Yes.
and G is injective from B to A, so both injective, then as it should happen, if theory is nice,
Then there exists
right?
bijection.
Then there exists a H, let's say, bijection, a bijection. Right. Okay. So we will try to prove this, but obviously, if you don't have an idea, then it will be difficult for you to think how to start. So let us see. Okay, let me try to, because I know a few things here. So let me try to say, and then we will try to complete this together. Have you ever thought about proving this?
No, sir. Like I saw proof once on Wikipedia,
Huh?
and like you said, it used fixed points, and like it was a short proof,
Okay,
and
if task
I
is
tried.
okay, may be that may be very abstract, right?
Yes. Yes,
That
I was.
yeah,
Yeah.
that is no, that is using, so there is a proof by using what is called Tarski's fixed point theorem. Okay,
Yeah. Yes. Some fixed
so
points they were talking
right,
about.
one fixed point theorem, which is that if f is a continuous function from 0, 1 to 0, 1, then there is a fixed point. Right.
Okay. Yeah.
F
Yeah.
of x there is a point where says that f of x naught goes to x naught, right? And there are many fixed points in mathematics, many fixed point theorems in mathematics. You'll do in linear algebra. Matrix is also fixed point. There is some vector which does not move, whose output remains the same. But then there is Brouwer fixed point theorem, which is basically like if you are stirring coffee in a
Yeah.
cup,
Yeah.
then
Yes, I've seen that. Then there's
yeah,
one point that
which doesn't move.
remains in the same place.
Right.
Yeah.
So that's another fixed point theorem. And
And
Tarski's
like they
fixed point.
also use the map example. Like suppose you have a map, then there's
Hmm.
always one point on the map that is exactly above the point it represents. Because the map is like
Correct.
a continuous deformation of the what can you say? Like the land,
Of the
the
land,
area.
right? Exactly. And it goes into it. So it's a function. Yeah, it's
Yes.
a deformation, as you already said. And then there is a point which is fixed. Exactly. So Tarski's fixed point theorem is also like that. And then basically these sound very different, with different theorems. But there are some theories which sort of unify them. Okay. I don't know actually to how much extent, but these are there. Okay. So anyways, but we will not use that. That is a bit technical. Okay. To be honest, I don't remember the Aske's fixed point theorem carefully. Okay. Clearly. But I have studied that at one point. So. But anyways, we will do a proof which uses an idea from graph theory. Okay. And it can
Okay.
be later converted into a problem in graph theory also, which you can try. Okay. But let us get going. So yeah. So let us say that if we start with a point A naught, okay, and we are trying to construct a bijective function, okay, but we will first start with a point A naught. and basically see to what extent we can, make a make a bijective function. Just 1 second, this alarm is ringing.
Yes.
So we will take this thing and we will see how far we can go with this. So what do I mean by this? The idea is this, okay? We take a point and we see how much of the function, how much of that bijection which we want to make, we can make using this 1 point. So, so where would you send it? There's not much choice, right? F of a naught.
F of a naught. Yeah.
And now where would
So,
you send?
okay, yeah, sorry. Yes, so the left set is A then.
Yeah, I did not write.
So, but since we're trying to make sort of like a bijection, shouldn't we send it to H of A naught? Like,
Yes,
because you
but we
said we're
don't know
trying to.
H. But we don't know H, right?
Okay, so like that. Okay.
So this will be actually our H of a naught.
Okay.
Because why not, right? This is a good choice.
Yeah, I mean, we already have a point,
Yeah, and
so
it's part
going
of
to
an
one unique
injective.
point.
Yeah,
Yes.
and 2 points won't go to 1 point by this F. So whatever
Yes.
we can send, we'll send, right? So now what do you do? Now we go, I mean, just as you can expect, we go to G of F of a naught,
F. Yeah, G of F.
right? So we go to G of F of, no, G of F of a naught. Okay, and then we keep continuing this, right? What happens if you continue
So
this?
we keep composing.
Right. Then we go F, then we go G. Now tell me what can happen in this kind of process.
So seems like anything can happen, but since you're
It's
saying that something interesting happens, I think does it go back to A naught at one point
it may
or
or may not. So let us take the case in which it goes back to A naught, right?
okay.
Let us take the case in which it goes back to A naught. So case one, the sequence is cyclic,
Yeah, goes back to A naught.
goes back to
Sort
A.
of terminates
Right.
or keeps repeating.
Yeah. So that's the other case. So if it goes, and then at some finite stage, it comes back to A naught.
Yes.
And this coming back to A naught means that it is happening via G.
Yeah.
Right.
Right. From B to A.
Right. Correct. Now let me think.
Yes.
Yes. So in this case, what this is a nice situation as you can feel. So in what way is it nice?
Um. So like we sort of have a fixed point. So like G of F of or whatever like that
Okay.
sequences of A naught is equal to A naught. So
Now you're like Tarski. Okay.
yes, sir.
It's a fixed point. Yeah, that is true. That is in that way it is nice. But for our purposes, exactly for our purposes, that may be nice in some bigger way also. But for our purposes, you see that we get a bijection on this small part.
Correct. Oh,
That you are okay with, right?
yes, sir.
Right? We get a bijection. For our
Right,
purposes, that
right.
is certainly good. Okay. Okay. Now tell me one more thing. If I start with now, if if we have exhausted all the vertices of the set, of both the sets, then it's fine, right? We can go home.
Yeah,
Then it is
true.
fine. But otherwise, if there is something which is left, okay, some A1 that is left, and if I do the same process in that, right? If I take a A1 and I do the same process, can it intersect with anything of the other, of that first sequence?
Uh, 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 no, because if it has to, then it has to intersect through F. But then F
Huh?
is injective, so
Yeah, so it cannot intersect. Correct.
yeah,
Correct. It cannot intersect. And this is basically because if it both injectivity of FNG,
yeah,
right? Both
injectivity of F and G.
both have injectivity, right? And it's basically like you have a graph in which the degree of any vertex is not more than 2. Something like
Yeah,
that, right?
yes,
It is, yeah,
something like
you
that.
can
Yes,
see that's what injectivity is here. Like 3 things cannot go. So everything breaks
correct.
up into cycles or paths.
Yeah,
That is the beautiful thing, right? The graph decomposes into disjoint union of cycles or paths. And this is a useful thing in from graph theory. That if your graph is such that every vertex has degree at most 2, then it's a disjoint union of cycles and paths. There cannot
okay,
be any
yes,
like cycles or paths. There cannot be because otherwise the degree will be more, have to be more, right? This is
yeah,
very useful. This is
true.
useful in all sorts of places. Semi-group theory, automata theory, graph theory, obviously, cycle decomposition of permutations. Like it's just useful. Okay, so right. So in this way, you keep whenever cycles come. So disjointness we have taken care of. Whenever the sequence becomes cycles, you are done. So now what should we look at? What is the case that we should look at?
When it doesn't terminate, like the
Right. So that's
sequence.
the only thing that we need to look at, right? Because we have taken
Yes,
care of the disjointness. So basically now the thing is I'm trying to say, which you already also see, is that we need to just focus on this, that I'm starting with a point and I'm doing this process, back and forth process. I'm getting an infinite sequence. On that infinite sequence, I need to show that both sides form a bijection.
yes,
Done.
yes, sir.
Because of disjointness and everything, that is the only thing we need to do. And cycle case we have taken care of. So then let's do that. So you're starting with some A naught and you're going like this, going like this. And it doesn't terminate. It doesn't terminate. So
Yeah.
then how do you, that can we make a bijection in this case? One thing is that because it doesn't terminate, you, given this A naught, you may have to also consider what to say. Is this coming from, okay, now again there are actually 2 cases. Okay, this A naught. So is this A naught equal to G of B naught for some B naught? Okay,
Um.
if this happens.
Okay.
And the otherwise you'll be missing some things, otherwise because you're only always starting from A, so you will never get to those elements which are in
Yes.
B, which are images like this. And in the other case is that A naught is not in the image of any B naught. Okay, so look at this case first. What can you say about this case? So basically A naught is sort of like the starting point. It is not in the image of any B naught, which in particular
Okay.
also means that the case doesn't terminate. So we are in good shape.
So
You
it
see, this is
doesn't
also
the
a bijection. Okay, go on.
so the sequence it doesn't terminate,
Doesn't
and the
terminate.
starting point is not some image under G.
Right. So basically, it's a true starting point.
Okay.
Right. Yeah. This is
Right.
actually also done. This is also a bijection. You
So
can
how like
just send it. So okay, right. So okay. So you just need some notation. So you take this A naught and call this B1, call this A2, call this should I call this B3 or B2? Let's call this B2, okay? And then A3, B3, and so on. So now here, what will your H be? Your H will be, means on this will again be a part, right? A partition, right? This will be a part in
Yeah,
that partition that we are talking about.
defined by a naught.
Right, defined by A naught. Now in this case, you just send H of AI to Bi plus 1. This is a bijection.
Okay.
This is a bijection, right? Because every Bi plus 1 is coming from some AI because it's not terminating.
Right.
And
Yes, sir.
it is an injection that is obviously clear.
Right. Yes, sir.
Right? The way we have done it, it's an injection. Right, of course. I mean, yeah. So done. So that case is done, right? Okay, now what about this case?
Okay, so when a naught is hmm.
Hmm.
So then do we so we have like the same argument, but instead of so then we have a bijection from B to A, we could say.
Yes, kind of, right? Yeah. So you just say that, okay, this is in the image of something, right? And so you have
Right.
this. But then it's good to just continue this in these kind of problems, right? It is good to just, if it's coming from some F, right?
Right.
So you continue it, right? Because see, if you don't continue it, you will miss this A minus 1 forever, kind of.
Hmm.
Right? I mean, if you really want it to be a partition, then you have to continue it backwards.
Correct.
Just
Yes,
think,
sir.
if you don't continue it backwards, then at some point when you consider this A minus 1, then in that sequence, these AIs will come actually, right?
Okay, right.
You can understand. So it won't be, so basically for mathematical reasons, you have to continue it backwards. Means there is no
Okay,
other way
yes, sir.
for things to be,
Yes,
for
sir.
it to be a partition. Like if I really sit down and try to prove that it's a partition, then I have to continue it backwards.
Yes, sir, I got disconnected.
Yeah, but then you get it right, that so
Yes, sir.
continuing backwards is important, and basically that infinite sequence is a bijection on its own,
Right. Yes, sir.
right? So basically we are done, right? See, in the initial case, we did not continue it backwards, because actually in that case it would have not, so when it was cyclic, when
Yeah.
it was
So
cyclic
like there's we can't continue it
yeah,
backwards.
actually,
We would just
exactly.
end up in the sequence itself. Like
Yes, yeah, there would be no backward image, right?
yeah.
Because of the, so we didn't have to. But if you want it to be a bijection, then you have to continue it backwards. Okay? So I mean, sorry, if you want it to be a partition, then you have to continue it backwards. So that's it.
Yes.
And then you basically
Yes.
on each part, this is a simple thing, right? If you think about it now. If you think about it now,
Right.
right, it's just that this is the situation where you have a graph in which really what is happening is that the degree of the vertices is small, it is at most 2, right? And then basically the graph splits into cycles and paths, and obviously cycles and paths may, the bijection is trivially happening. That's it. It's very simple.
Right.
Yeah.
Yes, sir.
And that's it, right? I mean, just the bijection between the vertices, and it's just the bipartition of the graph, pairing of things. It's just, that's all Schroeder Bernstein is. Okay. So yes, that's it. It's just this infinite graph theory kind of.
Infinite graph
Yeah,
theory. Yeah.
infinite graph theory, right? And this is also called infinite combinatorics, where there are a lot more interesting things which I don't know. They study many things.
Okay.
Yeah, it's a big area. I don't know what they do. So yeah, okay. So then let us stop here.
Right. Yes.
So today
Yes,
we,
sir.
yeah, just, but these are some techniques which you understand, right? In general, like doing things to partition and this, that, right? They help you to get things cleanly done. Because see, although
Yes.
mathematics is a creative subject and there are many solutions, right? But a lot of times you see that, means those solutions have some, you know, there is something about the problem which also tells you, right, what to do. mathematically, that okay, I should consider an equivalence relation, or I should consider a partition, right? Some
Right.
construction, some
Yes.
definition which you introduce, which really makes it easy. So yeah.
Right.
All right. Okay, then let's see. We'll meet tomorrow most probably. Okay, at 7:30.
Same time, sir.
Same
Okay. Yes.
7:30. Okay, and in case I need to change, then I will tell you. Okay,
Okay.
and
Yes,
obviously
sir.
that is there, and then Tuesday 9 Tuesday 9:30 in the evening. That is there. Okay.
Okay. Yes, sir.
Uh, Tuesday is Mahavir Jayanti also, but we do not celebrate that. Oh, so yeah.
Right. Right.
Do you
Yeah.
celebrate that? Are
No.
you
No. No. No.
Jain?
No,
Okay.
sir.
No. Okay.
No, sir. I'm not Jay.
Okay. Then we'll go on Tuesday also.
Yeah.
Tuesday
Yes.
9:30 is
Tuesday is
obviously
fine.
fixed. Yeah.
Yeah.
Okay. Maybe Tuesday
Okay,
we
sir.
can do some problem solving apart from matrices
Yes.
also, because today we did not. Okay, then
Yes,
you
sir.
continue doing it and you try to see where is it that you're lacking. Yeah. Try to understand the things. Is it speed, or is it
Yes.
something else, or is it
I
right?
think speed, sir, because most of the questions I attempt, I'm
Mm-hmm.
getting like the proper solution, but I take my time with it. Like I read one question and I switch on the TV and like
No.
sort of and then I
Okay.
think about it and then I get it. But then like the thing is, even when I sit and do it in a timed fashion,
Hmm.
I take like 15 minutes per question in part B
Right.
for ISI CMA, which I
Right.
think is fine, but I still feel like my speed is one
Right.
factor.
And see, you can see that very easily you can improve. Okay. Very
Okay.
easily you can improve, and one very easy way to improve, as you can already see, is just cut out the sort of the sources of entertainment.
Right,
Okay.
right.
Because see, point is that you like to solve problems, right? You like mathematics, right?
Yes,
So that itself is good enough, right? So you need to like less stimulus around. Okay.
right.
So like the strategy we follow, like when we are studying, and because mathematics is in the beginning it is boring, right? I mean, anything you start, anything, right, in the beginning it can be a little boring. Okay. It's not, mathematics is
Yes,
not the most exciting, like it's not the most exciting thing, right? It's not easily excitable thing. It needs effort, right? So that's why
correct.
you
Yes,
need to so that's why we cannot compare it with some good food or some entertaining movie. I think it's difficult, right? Those things are always more entertaining in the short term. So that's why what we do is like we try to cut out the electronic sources. Okay. Like sitting in a library with just a book. Okay. And you see, when you're just sitting with just a book, or not even the laptop, okay, most of the time we feel that we need a laptop to study the internet and so on. But actually, for at least 70% of your studies can be done without using laptop, right? Actually,
right.
okay.
No,
So
so
if
like what I meant was when I sit to study,
Mhm.
like I study with pen, paper, book, nothing else. But
Right.
sometimes I encounter like one question that it's taking me more than 15 minutes, more than
Huh,
20. So
that
at
is
that
right.
point, I abandon it. And then like
Oh,
it'll come to me randomly
ha
later.
ha
So
ha.
like I'll
Right,
be
right. Yeah, but that is not enough for an exam, as you know. Right.
correct. Yes,
Exam,
sir.
it has to sort of come. So that's why you need to train yourself to, to partition. Like when you're studying, you should only be studying. Okay.
Okay.
And yeah, like bring out more of the hunger. And for that, you have to you have to sort of tell your mind that there's nothing else around you. Okay, like there's no TV, there's no internet, and there is no, okay, for that time of when you're doing. After that, you can obviously go back. Okay, that really helped me when I was preparing for my integrated PhD exams, right? It's like I just did not carry my phone to the library. It was just 5 6 hours just without anything, and I did not miss it. Okay. But when it's there in front, then
Right. Yes.
I always check it, at least for me. So
Yes, sir.
yeah, yeah. So then maybe you will get more and more efficient, more and more like hungry for
Yes.
the problem. So when you see it, you're actually trying to solve it. Okay.
Right.
So yeah,
Yes, sir.
and also try to practice more MCQs. Okay, because you have
Oh yeah, I got
strategy.
the ISI tomato book, so it's full of MCQs.
Yeah. So do
Like
it.
every day I sit and solve at least like
Right.
20, 30
Yeah.
questions.
Right. And when you're solving it, attempt those 30 questions in that time, and yeah,
Yeah, yeah.
do it more.
Like I give myself 90 minutes for 30 questions
Right.
right now
That
as
is
a objective.
Yes. Yeah. Because because you can do well. That's what I'm saying. Just to, do it in the right way. Okay.
Right. Yes, sir.
So yeah, practice more MCQs. Okay. And yeah, that's
Okay. Yes, sir. Yes, sir. So
okay.
we'll
And
meet tomorrow at 7:30.
yes, yeah, and also when you are like these arguments, which they also reflect upon how to become more efficient. Not that's not same as seeking shortcuts, right? But how can you become more
Yes.
elegant in your argument? That you have to reflect when you're not studying, right? The difference is really that people who really do well or can experience mathematics more deeply are like when they're not doing mathematics, then also they are thinking some way or the other. It may not be
Right. Right.
directly about that problem, or they're not directly recalling the proof or directly trying to find the way to solve the problem, but they're also reflecting about, what are they doing that can make them, that is sort of, stop keeping them back and so on, right? They can constantly reflect about those things. Okay, so that you have to also
Yes.
do, right? Because you are the best person to solve your problems, right? Your
Right.
habits and everything, so you have to reflect upon your what are it may be very small things, very very small things that we do that keep us back, that only you can know, and you will have to reflect on them. Okay,
Right.
very small
Yes, sir.
habits, like even if someone has a habit of, let's say, itching themselves. Okay, it happens, right? When we get a hard
Yeah.
situation, we sort of start looking here and there, or some people have some very very small habits, which sound innocuous, but they really hurt. So you have to reflect on
They
those
add
things.
up.
Yeah, they add up. Okay, then yeah, we'll meet tomorrow.
Okay.
Okay,
Yes, sir.
thank
Thank
you.
you, sir.
Thank you.
Bye, sir.
Bye.